Okay, hello everyone, and welcome back to the Latin American webinars on physics. I'm Joel Jones from the PUCP in Peru, and I will be your host today. This is webinar 202, and we are having Marco Taoso as a speaker. Marco carried out his PhD at the University of Padova in Italy, which was followed by postdocs at Valencia, Vancouver, Paris, and Madrid. He then moved on to Torino, back in Italy, where he's currently a researcher. So today, Marco will give us an update on axion dark matter and show us how this scenario can be probed using observations of the sun. Now, before we begin, let me remind all viewers, as usual, that you can ask questions and make comments via the YouTube live chat system. And these questions will be passed on to Marco at the end of the talk. So, Marco, we are all yours.
Okay, so let me share first my slides and okay, tools, and ask you if you can see me well.
Everything good. We're good to go.
Okay, so first of all, thanks a lot for the invitations, and I also want to congratulate with you, Joel, and also all the other organizers of this great initiative. And as you remind, you have already hosted a lot of webinars, so you are performing extremely well. So thank you. And as you said, my talk today will be about probes of axions with astrophysics. So this is the plan of the talk. So at the beginning, I will provide a very brief overview about axion and axion-like particles to motivate them. And then I will go through basically few works that I've done recently on axion searches with X-ray observations of the sun. This will be the first part. Then I will also use solar observations or better prospects for future solar observation, but with radio telescopes. And it will become clear during my talk why I'm moving to this different part of electromagnetic spectrum. And finally, time permitting, I will discuss a recent work that I've done about searches of axion dark matter decays with X-rays. So let's start. First of all, why axion? So axions theoretically are motivated by the so-called strong CP problem. Probably many of you in the audience already know quite a lot about this, but let me just say a few things. So the strong CP problem stems from the fact that we expect in the standard model Lagrangian this kind of in terms. G mu nu is the field strength of the gluon, then we have the dual, and these terms are parameterized by a constant theta bar, which we cannot predict, but in general this term is there. And these are CP violating terms, and the phenomenology, the consequence that it predicts an electric dipole moment of the neutron proportional to this theta parameter. We do not observe an electric dipole moment of the neutron, therefore we have upper limits which are extremely tight. So the question is why? Why there is no such a term? We do not observe such a term. Okay, so it's a sort of fine-tuning and we would like to have an explanation. And of course, the most elegant solution is the axion. So the idea is to promote this theta term to a dynamical variable, so a field, which is the axion. So this is introduced thinking about a global symmetry, which is posternally broken at a very high energy. So it delivers a pseudo-Goldstone boson, which is the axion. And this symmetry should have an anomaly with the strong interaction, and therefore this anomaly gives such a term. So A is the axion field, and F is the axion decay constant, parameterized in the scale at which this symmetry is broken. So in practice, it's already clear that this theta parameter is basically now becomes this combination, this relation between axion and this K constant. So it's promoted to a dynamical variable. So the key point is that these terms at low energy when QCD confines produce a potential for the axion, which minimizes at zero. Therefore, whatever is the value of the axion field early in the universe, then automatically should relax to zero, and therefore this effective theta parameter is relaxes to zero automatically. So that's why we do not observe this term. So this potential provides a mass for the axion, and from calculation it turns out that the mass is related in this way to the axion decay constant, is inversely proportional. And if this axion decay constant is very large, so axion emerge from a symmetry broken at very high energy, then automatically the axion is a very light particle and can be can have a mass much below the electron volt scale. Okay. So this is a very light and very weakly interacting particle. In general, it can interact with all the kind of standard model particle that you have. So this is the effective Lagrangian of axion with at a scale below the electroweak scale. So axion will talk to gluons and also interacts with photons and standard model fermions. Okay, and also all these interactions are suppressed by this high energy scale Fa. Particular below the QCD scale, the interaction of axion with gluons and quarks generates interaction with protons, neutrons, pions, etc. So the second motivation, which is perhaps the most relevant one for this talk, for axion is the fact that axion is an excellent cold dark matter candidate. So first of all, from this diagram, we see the axion in general we expect to decay. But this decay rate is extremely suppressed. It goes like with the mass to the cube divided by this decay constant square, but also the mass is inversely proportional to the decay constant. So basically the point is that this decay constant is very large, and so this decay rate is extremely small. So the lifetime of axion can be much larger than the age of the universe, so the axion is stable on cosmological times. The other important point is that there are built-in mechanisms in this scenario to produce axion with the correct abundance in the universe and also cold, so non-relativistic. So we want cold dark matter. So there are the famous misalignment mechanisms, string production. I won't discuss them. I just mentioned that they are there, and that's why axion is a good dark matter candidate. So how we can detect axion? And most of the experimental strategies rely on the fact that axion couple also with photons through this Lagrangian term. F mu nu is the field strength of the photon. And this coupling G here is a coupling constant. So here we see that this coupling constant again, it has this suppression on this high energy constant Fa. And in the parentheses, we have two contributions. The first one is a contribution from, say, it's a model-dependent contribution. So depending on your particle physics model, which generate axion through this spontaneously broken symmetry, you can have some anomaly coefficient with photons, and then we have certain contribution to these terms. But there is also another contribution which is model independent in the sense that by construction, axion should couple with gluons, and therefore unavoidably at a certain point should also couple with photons, okay? So my message here is just to say that this coupling of axion with photons is expected. And this coupling is also can be written in this way as a coupling with electric and magnetic fields. So this leads to the phenomenon of axion-photon oscillation. So if I have an axion and an external field, can be electric field or magnetic fields, an axion can be converted into a photon and vice versa. Okay, so that's the way in which laboratory experiments try to generate photons from axion or axion from photons, say. So this is the parameter space for this coupling versus the mass, and all this is taken from a famous repository in axion physics, and there are many color regions which are excluded the region parameter space by laboratory experiment in red or astrophysical cosmological probe in green and blue. There is also a yellow band which basically gives the predictions of the coupling of actions, a function of the mass for the QCD axion, so the particle that discuss. Remember that here there is a proportionality between the coupling and say the mass, since the mass goes 1 over f. Okay, and of course one can have different lines depending on the specific model. It's also important to say that this is for some say minimal models, but there are also other non-minimal models, QCD axion models in the literature that moves these bands around this parameter space. Moreover, I want to introduce another concept, the concept of axion-like particles. So basically, this is a generalization of axion. So now you don't care maybe of the strong QCD problem, but you could still have some light scalar, like, I don't know, pseudo-Gosto boson from symmetry, which are similar properties, similar phenomenology, for instance, couples to photons, and you can populate different regions of the parameter space. So I think it's important to be open-minded and explore as much as we can here this parameter space, of course, keeping in mind a well-motivated benchmark like the QCD axion. So in order to introduce the astrophysical searches that I want to discuss, I think it's useful to discuss first a similar strategy that also will motivate the strategy that I'm going to focus with astrophysics. And this other strategy is the strategy of helioscope. So in particular, this cast is an helioscope experiment. So which is the idea? The idea is the following. So if axions exist, they are unavoidably produced in the interior of the sun, just because in the interior of the sun there is a plasma of photons, and therefore from photons you can generate axions. And I said that axions are very weakly interactive particles, so most of them will escape the sun without interacting, which means that we expect a flux of action reaching Earth. And this cast, in general, helioscope experiment aims at detecting axion, converting this solar axion flux in magnetic fields. They use magnetic fields of roughly 10 Tesla over 10 meters. So the axion arrived there is that through these magnetic fields in converting into a photon, which will be an X-ray, and then there is some X-ray detector at the end. Okay. So to predict our signal rate, we need two ingredients. One is the flux of action which reaches Earth, and another the probability to convert this action into photons. So first ingredient. So the first ingredient is known quite precisely accordingly to the current state of the literature. So this plot show the flux of action as a function of energy. Please focus only on these lines denoted by P. So this flux of action produced by this Primakov interaction. So the fact that from this kind of diagram, right? Interaction of photons and with electrons or ions inside the sun and leading to axions. And you see the spectrum is almost thermal, like because we have a sort of thermal bath of photons in the core of the sun, peaked at energy around few keV. That's why I was discussing previously about X-ray photons. And there are different lines which refers to different calculation with different solar models. And you see that uncertainty are small. Practice because this is from a recent paper, and practice because we think that the solar the conditions in the solar core are known quite well. For instance, we have solar neutrinos, which are a good diagnostic probe of the properties of the sun, with the temperature, etc., in the inner part. Okay. So first ingredient done. So now we have to compute the probability that an axion is converted into photons. So the formalism basically is take your Lagrangian, derive the equation of motions. You will find some modified Maxwell equation of motions. So since the fact now axion talk with photons, also the equation of motion of photon and Maxwell equation are modified. There are extra terms. Turns out that you can massage this equation. You have a coupled system of axion and photons with mixes, something like happens with neutrinos. And then in the case of an homogeneous external magnetic fields over a certain, which is denoted with a letter capital B, over a certain region L, turns out that you can compute the probability of conversion analytically, and is given by this simple equation. So this depends on the coupling constant and the size of magnetic fields. Of course, the extension, how large, the size also of the magnetic fields, how it extends in space, and depends also on this Q, which is the momentum transfer between the axion and photon. So here we are trying to convert an axion into a photon in presence of an external B field. So since axion is massive and photon is massless in the vacuum, there is a momentum imbalance, which basically is given by this simple equation in ultra-relativistic regime. E here is the energy, okay? So now we have two limits here. The case where suppose that the mass of the axion is extremely small, so this momentum imbalance is negligible, and then the probability of conversion is what is called coherent regime. So it grows quadratically with the size of the magnetic field region. However, if you grow, the mass of the axion grows, at a certain point we are in the opposite regime, and then the probability of conversion is suppressed, okay? So CAST have tried to observe this axion conversion. No photons have been found, and therefore we have only upper limits, which are shown here in this line in red. So this discussion basically explain a little bit why this trend. So a sufficiently low masses, probability of conversion does not depend on the mass. But if we increase the mass, at a certain point, CAST loses sensitivity because we enter into this incoherent regime. Okay, and that's why there is this trend over here. So I wanted to discuss this CAST limit because it helps to introduce what I'm going to discuss next. And so this is the idea here is to use X-ray telescope effectively as axion helioscopes. So why? So suppose now we consider this axion flux exiting the sun. This axion will pass through the magnetosphere, the atmosphere of the sun, which hosts a magnetic fields. So unavoidably, there is a small probability that they also be converted into X-ray photons. And if it is the case, we expect an X-ray photon flux from the core of the sun. So if we point at the X-ray telescope there toward the sun, we might observe a signal. So we can consider the probability of conversion as a quantity in order that we can exploit to compare these two different strategies. So a sort of figure of merit. So the magnetic fields in CAST is 10 Tesla. In the solar atmosphere is 0.1 Gauss. So here we have a huge suppression. But then the magnetic fields in CAST is over 10 meters. Now the magnetic fields of the solar atmosphere extends on scales of solar radii, and this overcomes the suppression, and therefore, in principle, we expect to have possibly a sizable signal. Of course, this is a very rough estimate, because then we have also to consider that one is a laboratory experiment, another is an X-ray telescope. There are different systematics, different backgrounds, and so on and so forth. But it's just to say that from this simple back on the envelope calculation, this seems a promising strategy. So how we can look for this X-ray signal? So we use an X-ray telescope, which is called NuSTAR. So NuSTAR, these are the main characteristics, the energy range, when it was launched. And basically, this telescope is not designed to do solar physics. It's designed to search X-ray from astrophysics sources, etc. But it also has the capability to observe the sun. And it has to look there. You see the field of view is not huge, so it has to decide where to look at the sun during a certain time. And NuSTAR conducted several observational campaigns. The most useful one for us was the one in 2020, because it involves significant exposure, and also the sun was observed during a period where it was close to the solar minimum. You know that the solar activity changes over years. So the solar activity can have maximum, minimum, and if it is at the minimum, of course, the solar is less active which is better for us since we are looking for a faint signal, right? So better not to have a strong background. So how we compute things? So we need to compute the probability of axion converting to a photon in the solar atmosphere. So now the magnetic field is no longer homogeneous. So this equation is basically a generalization of the first one that I showed. So it reduces to this one in the limit of an homogeneous field. It was derived, you see here, many years ago. So we need to integrate the profile of magnetic fields in the solar atmosphere. And then we have to take in account two things. One is the fact that now in the atmosphere of the sun, we are not in the vacuum. So this is important because in this plasma, there is a non-negligible plasma frequency, which is depends on the number density of charge, for instance, electrons, ions, etc. And this plasma frequency, you can think about the plasma frequency as an effective mass of the photon in the medium. So basically, this modifies the momentum transfer. There is also another term here, which in principle is relevant. So the fact that we are in the medium means that once the axion is converted into an X-ray signal, a photon, this photon can be in principle reabsorbed before reaching the detector, scattering with ions, electrons, etc. So we have to take care about this absorption, although this is not numerically particularly relevant, turns out. So we need these ingredients, we need the magnetic field. So since I'm not an expert of magnetic field, in our collaboration, in our paper, we basically in our team, we had some experts. So they basically provide us the status of art magnetic fields in the solar atmosphere, which is shown here. Okay, these magnetic fields are a function of the distance from the bottom of the atmosphere of the sun. Okay. And so it's basically divided in magnetic fields in different regions. So in this bottom part, in the photosphere, this is the status of art. So there are some hydrodynamic simulations which are tuned to some polarization spectral line signals in order to derive the magnetic fields. The bottom part is a more external part, which is the corona. We use the status of art is this simulation, you see a very complex 3D simulation, which was done in particular for the time of the eclipse, which in time is close to the period where NuSTAR observed the sun. So we don't expect a strong variation between two times. And was time during the solar eclipse, because when there is a solar eclipse, of course, the sun is the best condition to study the atmosphere, since the sun, you don't see it, and so you conserve the atmosphere better, okay? And then there is a region where so there are also other models which basically are in agreement and are supposed to be less precise. And okay, there is also a region where basically we interpolate between these two prediction of these two models, okay? Also the plasma frequency. So if you want, the plasma frequency is given by this equation, you see is related to the number density of electrons, and then, okay, there is also a quantity which is studies, there are models and tuned to observations, so on and so forth. So now, since we have this, we can do some predictions. And but first, let's go to describe data. So here we use so the observations of the sun have been performed in this way. So basically, there is a signal region, which is a circle at the center of the sun, with extending up to 0.1 solar radii. We call this signal region because we expect most of the axion flux coming from the core of the sun, since it's hotter, and therefore the signal, it comes from this disk. And then there is a background region, which is this annulus. And basically this background region is used as a control region to basically study background and then to extrapolate it into the signal region. So NuSTAR collaboration has performed, study of emission backgrounds of the solar disk. Turns out that sun is active, is producing X-ray signal, but the energy where we are exploring, basically most of the background is not from the sun itself, but some photons which are entering into the optics of the detector from outside. So this another kind of background which is supposed to be uniform. And so we can rescale this background from the background to signal region. Turns out that this rescaled background is compatible statistically with data, so we cannot claim any evidence for any kind of exotic signal, which means that we can only put some bounds, and the bounds are shown here in blue, which exclude this blue region, okay? So these bounds that are derived with the NuSTAR data. So in comparison, we see here the bounds from CAST, which are these lines here, okay? So this is quite an improvement if you think about that the flux, the signal flux scales with this coupling to the fourth power. So actually, if you traduce this improvement in improvement on flux, these are remarkable. And there are also some black line dotted and dashed. Basically, these are predictions, so future sensitivity of Yaxo and baby Yaxo, which are basically sort of bigger cast. So you see that in practice, this technique remains competitive with baby Yaxo, at least for some masses. I also need to mention that there are further constraints from astrophysics, and here they shown here. There are a lot of lines which refer to many of these constraints, and they come from a variety of things. I don't know, observation of cluster of galaxies, neutron stars, and all this kind of stuff, okay? So my message here is that this might be stronger, but these constraints are, I would say, still complementary, in the sense that some of these astrophysical environments are not that known as the sun. So comparatively, the sun is a quite better known environment where systematics related, for instance, to the knowledge of magnetic fields are smaller than other of these astrophysical bounds. So it's sort of, in my view, intermediate between some of these astrophysical constraints and, of course, the constraint from CAST, where it is a laboratory experiment, so things are much more under control, of course. So recently with Tiziano Zanzarella, PhD student in Torino, we have extended this work taking account that in axion models, as was motivating before, axion couples also not only to photons, but also to electrons and nucleons, protons and neutrons. So this coupling could contribute to the production of axion in the sun. For instance, coupling of electrons, which produce axion from this variety of process. And this is the axion flux produced in this way. For the neutrons, for the coupling to neutrons and protons, actually it has been pointed out since many years that this energy, the most relevant things that we can look at is an axion line, so sort of monochromatic axion emission produced by the excitation of this 57 iron. So this iron is present in the core of the sun, can be thermally excited, and then de-excite. Most of the time we de-excite into the ground state with a photon, but there is a small probability de excite producing an axion through this coupling, okay? And the excitation line is a 14 keV, which is in the energy window probed by NuSTAR. So again, we have, if you want, three parameters: this axion coupling to nucleus or electrons, the axion coupling to photons. We still need to convert axion into photons in the atmosphere, and then the mass. So we can do this kind of plot. So plots on the products of axion coupling to electrons and photons versus mass, or study the parameter space of the other two. And again, these are the general comment that I have here. These constraints are competitive with the laboratory experiment in both cases of axion electron, axion nucleon coupling. And of course, there are other astrophysical bounds that are not shown here. I can show you if you are interested, which cover this parameter space, okay? So this is all what I wanted to say about searches of axion with X-ray solar observations. Now I want to briefly discuss this other possibility, the possible detection of axion dark matter around the sun. So the previous discussion, I never mentioned dark matter because these axions are there regardless if they explain the dark matter of the universe or not, since they are produced in the interior of the sun, relativistically. But now let's make the extra assumption that axion is dark matter. So if it is there in this dark matter, it should be also around the sun, and therefore it can be converted into photon in the solar atmosphere. Of course, the situation is very different because previously we have a relativistic axion producer with typical energy of keV. Now we have a non-relativistic axion dark matter with negligible kinetic energy and with energy which are related to its mass, rest mass. And here we are discussing axions which are ultralight, and therefore you can think that the photon produced by this conversion won't be an X-ray photon, will be a low energy photons. In particular, it will be a radio photon. That's why I invoke radio telescopes to search for this signal. So potentially there is a problem here, which is known in this literature, the fact that the conversion of non-relativistic axion in the vacuum, or I mean, it's in astrophysical environment, if it is in the vacuum, is quite suppressed. So coming back to the previous equations, we know that this probability of conversion should depend on a length scale. But if the axion is not relativistic in practice, this length scale is related to the inverse of its mass because we are in this incoherent regime, right? So this length scale is small. It turns out the probability of conversion is quite small, okay? If you want, you can think about the fact that in astrophysical environment, there is no such, the magnetic fields have not fluctuation at a small scale such to lead to a momentum in the vertex to pair this imbalance of momentum. Well, there is also a way out, which is proposed already years ago and exploited a lot in the literature, especially in the constraint of a neutron star, which is the following. Situation can be different if the conversion happens in an astrophysical plasma, which often happens, right? So why it is different? Because in a plasma, the photon dispersion relation is modified, and the photon in a weakly magnetized plasma, the photon dispersion relation is such that the photon has an effective mass, as I said before, which is the plasma frequency. So let's take the plasma around the solar atmosphere. This depends on electron number density, so it decreases when we go farther and farther from the sun. So there might be a point, a radius at which this plasma frequency is equal to the mass of the axion. So at this resonance point, a resonance happens since the fact that the plasma, the photon and the axion has the same dispersion relations means there is no imbalance of momentum, and therefore we fix the problem that I was mentioning before, okay? So there is an enhancement and the probability of conversion can be boosted, okay? So this happens when it depends on the axion mass. For a given axion mass, this happens at different points in the atmosphere. You can take the plasma frequency on the solar atmosphere, and therefore you have a range of masses that you can probe. We will be around the microelectron volt level. Okay, so this is the probability of conversion now. This formula which has been produced in the literature from this kind of stuff basically depends on properties of the plasma and the magnetic fields at this conversion radius, okay? Which is the signal. The signal is a monochromatic photon, differently from the previous case, since we are converting a particle at rest. And as I said before, is a radio wavelength photon because of that's the properties of the plasma frequency in the atmosphere of the sun. So we want to look at this line. And so this is a radio line at a frequency equal to the mass of the photon. Okay. And so what I present now, there are some prospects, are not limits from real observations, but are prospects for future searches. Particularly, I'm focusing on SKA, the Square Kilometre Array telescopes. So it's an array of telescope which is going to happen soon, is under development, and there will be array of telescopes in the South Africa and also in Australia, I believe. And so we try to see which are the prospects to detect these radio lines with the SKA law. So basically, our prospects are based on sensitivity to radio lines, anticipated performances by the SKA collaboration. We have to rescale this sensitivity, taking account the fact that we have some backgrounds, degradation, because we have some angular broadening of the signal, some technical details, okay? And these are the sensitivity in the plane coupling versus mass. This is the black line, and are compared again with bound from helioscope and astrophysical bounds. So there are some regional parameter space that you can principal probe over there. So these are very tough technique because the signal is very faint, but according to anticipated performance KA, there is something you can do. So there are a few lines here because also when we did this paper, we try also to play this idea of considering solar sunspot. So we know that in the case when the sun is very active, in the atmosphere of the sun, there is the so-called sunspot, which are regions with strong activity. And around this sunspot, these are localized regions, so they might be small, but the magnetic fields there can be extremely large, much larger than the usual global magnetic fields of the sun. So we are sort of excited to see maybe if we have a strong magnetic field, then this can boost our prospects for detection. But it turns out that actually this is not the case because there are also non-trivial absorption effects in presence of a strong magnetic fields. When the radio signal is produced, then can be absorbed by cyclotron absorption. Simply the fact that electrons in a magnetic field have some Landau energies, and then they can absorb a photon passing through. And basically, it turns out that is also killing the signal. So it turns out that actually, if you have a strongly magnetized region, most of the signal doesn't go out. So this, in practice, this we cannot do much better than this. So passing through, I think it's important that I discuss this kind of sensitivities also in the context of another dark matter candidate, which is the dark photon. And I should give credit to I.P. Yan and his group, which produced quite remarkable work on this. So the dark photon, I've not introduced this, but is also a light dark matter candidate. So it's basically a sort of photon which massive photon which kinetically mixes with the ordinary photon through a parameter which is this epsilon, which is small. So basically that photon couples to electromagnetic currents, and the coupling is suppressed by a parameter which is this epsilon. So again, also in this story, we can have oscillation between photon and dark photon. Now we don't need a magnetic fields, but we can have this kind of oscillations. And it turns out that we can map our sensitivity to the case of dark photon, simply changing this combination of parameters for the axion, so the coupling magnetic fields, into this combination of parameters for the dark photon. So this kinetic mixing and the mass of the dark photon. So if now I map the previous parameter space, the previous sensitivity for axion to the for the parameter space of dark photons, you see here that SKA now can look some relevant part of the parameter space which is currently unexplored in principle. And in fact, current observations of the sun with the radio telescope are already testing some region parameter space. This is a work using LOFAR, an existing radio telescope. The data set exploit only 17 million observations, so maybe something better can be done. And also there are some observations with this Solar Parker probe, which is a spacecraft which basically was sent into the solar corona, and so they basically had also some data there. Okay. So this is what I wanted to say about axion dark matter and prospects for detection with using solar observations, particular radio solar observations. Now I'm going to finish in a few minutes just discussing very briefly another possibility. Up to now, I have discussed only the possibility of conversion of axion into a photon in a magnetic field, in a stellar magnetic field. But in principle, axion can also directly decay into two photons. I was motivating before that this basic decay rate is extremely small if the axion mass is small, right? Because the decay rate goes with the mass to the cube. But if I increase the mass of the axion, or if you prefer to call it different axion-like particle, then the decay rate becomes sizable, and this signal can be relevant, and this signal is basically a photon line. So actually, if you move the mass at electron volt level, the photon falls in the optical or near infrared band. And now we have used spectroscopic observations a few years ago about MUSE of dual spheroidal galaxies to put some relevant constraints. Those other groups have extended this with other instruments. So the message here, you see that these are quite relevant probe in the sense that this regional parameter space is hard to test with other probes. This is also true if we increase the mass into the keV range. Now the photon is an X-ray signal. And basically this is the same strategy used for decays to look for the decay signal of another dark matter candidate, which is the sterile neutrino, right? Sterile neutrino decay into an active neutrinos and photons. And relevant constraints are from this telescope, NuSTAR and the XMM Newton. And with Jorge Calvo in Torino, postdoc in Torino, we have tried to use some recent data from Rosita. So Rosita is an X-ray telescope which covers this energy range. So it's a soft part of the X-ray band, and it has, if you look at its effective area, field of view, etc., you compare with other telescopes, you see that it's competitive for energy around a few keV. The good point of Rosita is that it performs, works in survey mode, so you observe basically a large part of the sky, all half of the sky is available. So it's a perfect instrument if you want to do survey studies, etc., right? So there are now, there is a public first data release of Rosita data. Perhaps there will be more in the future. And we have used this data, published available data. We have analyzed them. And basically, we have focused on a specific target, which is the Large Magellanic Cloud, which is a large satellite galaxy orbiting around the Milky Way. We have considered this because it's fairly massive, and now we are considering, making the hypothesis that this axion is the dark matter, so it means that there is a lot of dark matter there. But this is also a relatively compact object in the sky, so it is a few degree, occupies a few degree radius circles in the sky. So from the point of view of data analysis, it's easier to have this kind of compact object to analyze. So basically, we extracted the flux beamed in energy from there, and Rosita have a very good angular energy resolution. So it's good if you want to see a line, right? So we have this spectra of from the Large Magellanic Cloud. We search for a line. there are technical details that I think it's better to skip. And then we didn't find any evidence for an anomalous line. So we are just able to put some constraints, which are shown here. So these are the constraints in the plane mass versus coupling. The gray band are from previous searches with X-ray telescope. So there is some range of parameter space where there is some improvement. Let me say that there is also possibility to improve this using a larger data set of Rosita, probably considering all the halo or moving to galactic center region, which is something that we plan to do in the future. Before finish, just 1 minute, let me say that this can be recasted, simply recasted for also in another context. So suppose that your axion is not dark matter, still these observations are useful, and this has been pointed out a few years ago in this paper. Why it is so? It is so because regardless of the fact that the axion is dark matter or not, if they couple two photons, they are unavoidably produced in the early universe. So there is a relic abundance coming from there, right? So this is a freezing production, standard model particle in the universe, scatters and produce some axions, which are there. So there is an irreducible axion background, and if these axions are long-lived, then they can decay now. Of course, their number density, their abundance can be extremely small, but also the coupling can be large. Of course, there is an interplay between coupling between production and then decay, okay? And this context these are the bounds that we can put in the parameter space. So basically the axion production, the relic axion production depends on the coupling, and we use the information provided by this paper. Once we have the axion background number density, we can compute the decay rate and compare with our data. And again, we can basically simply recast our bound in this more general scenario, which is valid regardless of the fact the axion is dark matter or not. And okay, so this is it. So this leads to my conclusion. So the main message is that the axion can be looked for with astrophysical observation. I've discussed three strategies. Using a putting bound from X-ray data, also X-ray observation of the sun, or maybe with future observation of the sun with radio, or observing the X-ray sky with X-ray telescopes. That's it.
Super. Many thanks for the very, very nice talk. I really enjoyed it. So this is a time for questions. So there is a lag between the session and the YouTube transmission. So usually we start with the general with us before going to the YouTube questions. I'd also like to point out that we have Eduardo Peinado here as a guest, who might also be asking questions. So yeah, the court is open. I don't know if there's any question from anybody here. Okay, so I have a question. So can you go back to your results of the first part of the talk regarding NuSTAR? That you compare it with CAST, right? So at some point in the talk, you say, oh yeah, you can see here that the limit of CAST degrades because you go to the incoherent regime, right? So here, I guess that you're also having something similar, right? That you're bound, and then you go into an incoherent regime, and then you have a suppression. But why does it happen at different points? Because I would have expected both of them to happen more or less at the same point where the mass exceeds a certain value.
So excellent question. Yeah, it's in fact it happens at different point because the different properties inside the sun. So this transition depends on the mass, the energy of the axion, which are basically do so, but also depends on the plasma frequency, because now differently from for the standard helioscope case, we have a plasma frequency entering here, and basically this modified these momentum transfers, and this plasma frequency is non-negligible. And therefore, you see, there are some masses for which basically it kills the probability of conversions. That's
see.
the reason.
I see. Okay. Okay. That was clear. Super. Thanks. Any other questions from the public?
Yeah, I have a question for Marco. Marco, very nice the webinar and the work. So I was wondering, is any chance that also this type of study can be done with ALMA, since it is a similar
With ALMA?
With ALMA, since it's a similar radio telescope that SKA.
All right. So okay, so I would say I'm not sure. So that has to be checked. It's interesting. So there might be some issues related to the fact that, you see, here in this part, I'm really exploiting this conversion probability, no? When the axion mass crosses the plasma frequency. So, and then, so this axion mass is giving the frequency of your radio photons. If now you move to ALMA, you move to another range of frequencies. So you have to see where this falls here. Maybe this is higher energies, and maybe you don't have large enough plasma frequency in the solar atmosphere to do that. That I'm not sure. So it might work or not, I don't know.
Okay, thank you.
You're welcome.
Maybe a follow-up question on this, sorry. But then in some sense, Marco, you can do dedicated telescopes at a particular frequency, right? And maybe and then try to just fill up the gaps with because I think whenever you observe the sun, you don't necessarily need huge telescope or something like that, right? And
yeah. This is true. So
so there could be small mission proposals that are just targeting a particular band for something.
Yeah, exactly. So I'm scared that you cannot prove too much, in the sense that there are some limitations. For instance, one thing that I didn't say is, or I said very quickly, is that for radio photons, once you produce in the interior of the sun, then they also have to escape, and there is an important, there can be an important absorption effect. Okay,
Yeah.
and these absorption effects, it depends where on this photon is produced. So depending on the frequency of your radio telescope, you are probing different masses. So basically you are probing photons produced in different regions. And there are some range of masses where, unfortunately, thermal Bestrahlung, absorption from thermal Bestrahlung kills your signal.
Mm-hmm.
Okay, so there is part of this parameter space that I know that is tough because this reason. Because you produce the radio photon in a region of the solar atmosphere where absorption is very strong, actually. Then usually problem of going to smaller masses is that at a certain point is very difficult. Basically, it's impossible to observe something outside the atmosphere with a very low frequency, right? So basically, the photons are reflected by atmosphere, so that's an issue. And in fact, here, basically, the solar power code is good because you observe this small frequency because it's outside the atmosphere, right? So this is also... But yeah, in general, I agree with you. So more than, I mean, if you have something similar to this, or you see we probe different bands, then we can do some scan here. And yeah.
Thank you.
Super. Any more questions? Let me see if there's anything on the YouTube. No, nothing so far. I have a very basic question regarding the stability of the axion dark matter, because yeah, I noticed when you addressed axion decay into 2 photons, said, then axions are not dark matter, then you should have another dark matter candidate, But then you said that you did. So then we're now in the scenario that the axion must have a long enough lifetime, right? Such that so it can still be dark matter without decaying into photons. So is this generally the case in all of the parameter space? Do you always have the axion long-lived enough such that it can be a dark matter candidate?
Well, I would say that it's so in this parameter space. Let me go maybe to this initial here. So there will be some region parameter space where it happens, where it is not, right? So here it is. Probably if you go to large coupling here, it is not, actually. So now that you tell me this, for instance, one thing that I didn't say that is there. In this scenario where you have this relic axion background, you see that I'm putting some limits. And there is an open, my limits are not excluding all parameter space, but then the curves close. Why close? Precisely for what you say. Here we are pushing the coupling so large that practice these actions are no longer there. I've already decayed, so we cannot test this. So it's excellent,
Great. Yeah, I'm happy. I don't know if there's any last questions, Roberto.
I have one, but it's very out of the box. It's not. I mean, because usually when we have some webinars in which they talk about gravity in some extra gravitational models beyond GR, there are a lot of action-like particles or action fields involved with gravitational waves and so on and so forth. It would be a way to connect some kind of because here is kind of an effective coupling because we're motivated by QCD, but to motivate also with some couplings to gravitational fields, not in the sun, because for that reason I'm saying out of the box. I don't know.
So
sources
coupling
of
of
action from black holes or merger of neutron stars or something like that. That usually there are these extreme processes that could produce maybe that type of actions and not the one from QCD.
So I'm not an expert enough to give probably a clear, a complete answer, but on the top of my mind, I'm thinking that there are some scenario where you produce action from some gravitational waves, and an example is, I think, this super radiance. You probably have heard this effect where you have a black hole which is spinning, and because of GR effects, actually you source the production of action. This action comes from at the cost, at the expenses of the spin of the black hole, which slows down. It doesn't involve necessarily the fact that action is dark matter or the action couples to photons, just the fact that it's a generic. So it's even beyond action, I think. So that's a possible connection that I have in mind. And in fact, from observation of spinning black holes, through this argument, it's possible to put constraints on axions, actually. So they have been derived, and I know that there is an activity in the literature about that. Perhaps there are more general things that one can think about if we think carefully, as you said, maybe related to mergers of black holes. I don't know. But it's an interesting topic, of course.
For that reason, I said very out of the box. Thank you.
You're welcome.
Super. So this is a good time to close, I think, unless there's an urgent question. I can accept a non-urgent question also. Okay, super. So thank you very much, Marco, for the wonderful talk. It was very, very, very clear. To all of the viewers, I remind you that we are still having one more webinar before our winter break. In 2 weeks, we're having Andreas Krivelin giving us a talk on collider hints of new physics just before the conferences. Okay, so please stay tuned and we'll see you around.
Thank you so much, Joel.
Thank you. Bye-bye. Okay, we're done. Super.